Hello, this is Joe Trout from the physics program at Stockton University. This chapter is chapter 16 and 17. It starts out describing how the sun generates energy. So if you look at the sun, it takes an incredible amount of energy for the sun to shine, and it has and will continue to do so for billions of years. When people first began to theorize how the sun is able to create such energy, the first thought was that it came from the sun's gravity, and that gravity was causing such a large compression that it was heating up the gases. So, for instance, William Thomas Lord Kelvin and Hermann von Helmholtz proposed that the contraction of the sun under its own gravity might account for the energy. Then came about Albert Einstein, and he started to learn a lot about energy. He found out that the total energy in a mass is equal to the mass times the speed of light squared. So you may have heard E equals mc. And we started to work and talk about and theorize about exactly how the sun was able to generate such heat and light. We also came along Wolfgang Pauli, who theorized about the neutrino, which is a particle much like an electron, only it has a very tiny mass. It might even have a zero mass. So there's two ways to get energy from atomic nuclei. One way is by fission, and that's how our nuclear reactors work. So in fission, what happens is we take a relatively large, heavy, complex nuclei and smash a particle into it and break it apart, and we get lighter nuclei and energy. In fusion, which is how the sun works, what happens is light atomic nuclei join together to form a heavier nuclei, and this releases energy in the process. So A shows how the sun works by fusion, and B shows how our electric power plants work by fission. So if we look at the fusion in the sun and other stars, it starts with a proton-proton chain. And what happens is we start with two hydrogen atoms or hydrogen nuclei, and they fuse together into helium inside the sun. High temperatures are required because this reaction starts with two hydrogen nuclei, which are protons, and they're shown as blue circles to the left, that must overcome the electric propulsion they feel in order to combine and to form a hydrogen nucleus with a proton and a neutron, which are shown in red. Note that the hydrogen containing one proton and one neutron is giving a special name, deuterium. Also produced in this reaction are a positron, which is a positive electron. It has the same mass as an electron, only it's positive, and an elusive particle known as the neutrino. In step 2 of this reaction, in the second step of this proton-proton chain, the fusion reaction that converts hydrogen into helium in the sun. This step combines one hydrogen nucleus, which is a proton shown in blue, and the deuterium nucleus from the previous step. shown as a red and a blue particle because it's a proton and a neutron. The product of this is an isotope of helium with 2 protons and 1 neutron, and the energy in the form of gamma radiation. Next is the third step. In this step, the fusion of hydrogen into helium in the sun. So note that the 2 helium-3 nuclei from the second step must combine before the third step becomes possible. And the 2 protons that come out of this step have the energy to collide with other protons in the sun and start this whole step over again. ITER design, this is a bright yellow area, shows a model where superconducting magnets will circle a chamber in which fusion will take place. And the huge magnet will keep the charged nuclei of heavy hydrogen combined. And the goal is to produce about 500 megawatts of energy. So the idea is that we wanted to try fusion on the Earth, but it takes an incredibly amount of energy and heat. And in essence, we wouldn't be able to hold it in any container. So we'd start a large magnetic bottle, if you will. And that magnetic bottle will hold the charged particles. If we look at gas pressure, what it is that the particles in the gas are in rapid motion and they produce pressure through collision. So if you think about it, all the gas molecules in the room you're sitting in are moving around, and it's actually when they collide with things is how the pressure is formed. So for the stars, what would happen is we have a very hot center where this fusion is taking place. And if it weren't for gravity, that would push the star apart and it'd become bigger and bigger and bigger. However, the inverse force is pulling it in. So if we didn't have the pressure pushing it out, then gravity would keep pulling the star closer and closer in towards the center. And if it weren't for gravity, the pressure would keep it going, expanding more and more. So what there is an equilibrium. The pressure from the hot gas equals the force per area from the gravitational pull. And these are in balance, so the star maintains its size. If the star started to run out of fuel, what would happen is it would start to cool down and the pressure would decrease. And when the pressure decreased, then the star would collapse. Because what would happen is the gravitational force would remain constant because it depends on the mass, and it would pull all that material in towards the center. And we'll talk about that in a couple of chapters when we talk about the lifespan of a star. Don't forget, in the sun, or in any star really, we have convection, and we have these rising currents of convection that carry heat from the sun's interior to its surface. And the cooler material, which was sitting on the outside of the sun, sinks back down. Of course, it isn't as simple looking as what the book suggests. If you've ever seen water boiling on a stove, it's very complex, right? But generally the same thing is happening. The water gets hot when it's at the bottom of the pot near the flame. Then it expands and rises to the top, and the stuff that was at the top has cooled a little bit because it's radiating and conducting energy out to the atmosphere, and that part sinks down. But it's very complicated. But roughly, this is what we're seeing, these convection zones. The photons deep in the sun are moving through this dense gases in the solar interior, and it travels only a short distance before it interacts with one of the surrounding atoms. And the photons usually have a lower energy after each interaction, and they travel pretty much in random directions. So they're floating around in between these gas molecules and running into the gas molecules. So with the sun, we have these photon and neutrinos being formed through during the um, fusion, and because the photons generated by fusion reactors in the solar interior, they travel only a short distance before they're being absorbed or scattered by an atom, and they're sent off in random directions. And it estimates that it takes between 100,000 and a million years for energy to make its way from the center of the sun to its surface. In contrast, neutrinos don't interact with anything. So for one thing, they're very light, and for another thing, they have no charge. So what happens is they travel straight through the sun at a speed of light, and they're reaching the surface in a little more than 2 seconds. So the interior structure of the sun, if we look at the energy generated in the core by fusion of hydrogen to form helium, and this energy is transmitted outward by radiation and, in essence, by absorption and re-emission of these photons. In the outermost layer, the energy transported mainly by convection, as we talked about earlier. So if you look at the interior of the sun, here's diagrams showing how the temperature, density, rate of energy generation, and the percentage of mass abundance of hydrogen may vary inside the sun. So the horizontal scale shows the fraction of the sun's radius, and the left edge is the very center, and the right edge is the visible surface of the sun, which we said was called the photosphere. So if we look at the temperature, it's very high in the center, and then it drops off as we reach the surface of the sun. Here, where the temperature is greatest, we have nuclear fusion going on, and then the radiative zone, and then the convective zone. If we look at the fraction of luminosity, right, we see that it rises very quickly in the nuclear fusion region, and then it remains constant through the radiative and convective zone. The density, of course, decreases as we leave the center. And if we look at the percent of hydrogen by weight, right, we start out with a less than 50% at the center, and then it rises up as we move out towards the outer surface. So the density is pretty constant through the radiative zone and the convective zone, where it's lower in the center. We also see that there's oscillations in the sun. So as we look at new observational techniques, we can measure small differences in the velocity at the sun's surface, and we can infer what the deep solar interior is like. So this is a computer simulation of what we think it might look like. So when we have sunspots, we see the drawing shows off the new understanding of the helios seismology, right? So if you think of seismology on the Earth, we're talking about earthquakes and how the different land masses are moving, and we can look at this to understand that how sunspots are being formed. And for measuring neutrinos, since they don't interact with anything, what we do is they have to go really far deep beneath the Earth's surface. So if we look at Davison's experiment, what he did was at the bottom of an abandoned gold mine, and it first revealed problems with our understanding of neutrinos. And here shows the Sudbury neutrino detector. And if it's a 12-meter sphere, and don't forget you're about 2 meters tall, so it's about 6 times as tall as you, right? And this detector lies more than 2 kilometers underground and holds about 1,000 metric tons of heavy water. So, where does the heat of the sun come from? It comes from the nuclear fusion of hydrogen into helium. So you've probably seen this picture a couple of times already. Here we see that they left the camera lens or shutter open, and as the Earth rotates and we take a really long exposure, what we see is that we get these lines of the circular motion of the stars across the image, and it's provided by the Earth's rotation, right? And the various colors are actually caused by their different temperatures. So you see reds in there and white and blue. So if we look at the apparent magnitudes of well-known objects, so what we're talking about is how bright they are. And the faintest magnitudes that can be detected by the unaided eye, and then by binoculars, and then by large telescopes are shown. So if we look at, say, Betelgeuse, it has apparent magnitude between 1 and 5, right? And then the faintest object visible to the unaided eye has about 6, right? And these are the apparent magnitudes. So here's the 1 meter telescope limit, right? And if we look at the apparent magnitude of the moon, it's at about negative 12. And for the sun, it's at about negative 26, 27. So here we see the Sagittarius star cloud. And what you see is this is an image taken by the Hubble telescope. And it shows the stars in the different directions towards the center of the Milky Way. And the bright stars glitter and they have different colors. So the blue-white stars are much hotter than the sun, whereas the red stars are cooler. So on an average, the stars in this field are at a distance of about 25,000 light years. Don't forget, a light year is the amount of time, the distance it takes light to travel in a year. So this is 25,000 of them. And the width of the field is about 13.3 light years. So it was William and Mary Huggins who first identified the lines in the spectrum of a star other than the sun. And they also took the first spectrograph or photograph of a stellar spectrum. So don't forget, the idea is you take light and you pass it through a spectrum and you get, in essence, a rainbow. And they were the first ones to do this. So if we look at absorption lines in the stars of different temperatures, this graph shows the strength of absorption lines of different chemical processes. So don't forget, what we said is that if you had white light and you shone it into something, and any light that's not absorbed is either transmitted or reflected by the material. So if you had white light and a particular wavelength was absorbed, then it would show up as a dark line on the spectrum. So here we see spectrum of stars with different spectral classes. And this image compares the spectra of the different classes. So wherever this was all white light, and wherever a wavelength was absorbed by some material, then we had a dark line appear here. So this image compares the spectrum of the different spectral classes, and the different spectral classes are assigned to each one of these stellar specters that are listed on the left. So it starts at O and 6.5 and B0, B6, and A1, A5, F0, F5. Okay, and originally what these were just A through whatever, and then they were actually reorganized at a later time. So the strongest four lines seen at the spectral A1, right? So if we look at A1, we see that there's one in red and one in blue-green and two in blue. And these are the bomber lines of hydrogen. So note that how these lines weaken in both the higher and lower temperatures. So the strong pair of closely spaced lines in the yellow in the cool stars is due to neutral sodium, and this is one of the neutral metals. So Cannon is well known for her classification of the stellar spectra, which we were just looking at. So if we look at brown dwarfs, this illustration shows the sizes of surface temperatures of brown dwarfs that were hard to see before, right? And there's brown dwarfs, TD1 and Gliese 229b and Weiss 1828 in relationship to the sun. And a red dwarf star is shown, and also Jupiter. So the spectral lines, as we can see here, this figure illustrates one difference in the spectral lines from two stars at the same temperature but different pressures, right? So a giant star with a low pressure photosphere shows a very narrow spectral lines in the bottom, whereas the smaller star with a higher pressure photosphere shows a much broader spectrum at the top. So here we see the UV, and this is near IR, and this is the visible spectrum, right? And here this is for a white dwarf, and this is for a blue giant. Another thing we can tell from these spectrums, and Doppler radar works the same way, we see something called a Doppler shift. And if we look at a stationary star, we see it might have this spectrum here. And you see that there's a couple lines in the near ultraviolet and two lines in the blue and one line in the red. Well, when a spectral line, if the star is moving away from us, then what happens is we get a red shifted spectrum. So you see it has the same number of lines, but it's shifted over towards the red. And when stars are moving towards us, they get shifted towards the blue. So here's a stationary star. If we look at the spectrum and we see it's shifted to the red side, we know that the star is moving away. And if it's shifted in the blue direction, then we know that it's moving towards us. So these three photographs of Barnard's star and the star with the largest known proper motion. So it shows this faint star has moved over a period of 20 years. So here it was in 1985, and 1995, and 2005. And right, so this is the motion. These were all taken on the same day of the year at different years. So we see changes in the Big Dipper, for example. This figure shows the changes in appearance of the Big Dipper due to its proper motion of stars over about 100,000 years. So today, what we see is that some of the stars are moving in one direction, and a few of them are moving in the other direction. And this is what it looked like 50,000 years ago. But now, as these stars continue to move, if you think this one moves out this way, then the dipper will become a little bit wider, right? And the handle will become a little more bent, where all the other stars are moving in the opposite direction. So we're talking about two different things, the space velocity and the proper motion. And this figure shows the true space velocity of a star, right? So the radial velocity is the component of the space velocity that's projected along the line of sight from the sun towards the star. So here's the sun and here's the star, and it has some velocity. And we can break that velocity into two vectors, one that's transverse and one that's radial, right? And um, and the proper motion is actually this arc that's going to travel through mu. So what astronomers measure is the proper motion, which is the change in the apparent direction on the sky, um, measured in fractions of a degree. And then to convert this change into a speed, say kilometers per second, it's necessary to know the distance from the star. We can also use this spectrums. We can also use spectrum analysis to determine the stellar rotation, right? So if we look at the star the rotating star will show a broader spectrum um, lines than the non-rotating star. So if this star wasn't rotating, what we'd see is that all the light would come and we'd get this nice sharp spectrum with this dark line. What happens when the star is rotating is that some of them will be drifted, Doppler shifted, moving away, and this side is Doppler shifted moving towards, and we see that there's a broader a broader line here. So when we compare the rotating stars, right, this illustration compares the more rapidly rotating star Altair and to the slower rotating sun. So the sun, its rotation about 24 to 30 days, and Altair rotates at about 6.5 hours. So if we look at, here's a picture of Dapper standing next to a telescope used for photography. And after his death, the widow funded further astronomy work in his name. And Lick was a philanthropist who provided funds to build a 36-inch refractor, not only as a memorial to himself, but also as an aid to further atmospheric astronomical research. Okay, so that ends our lecture for chapters 16 and 17. And thank you for your time.